A little more information on an infinite geometric series. Reminder that a series is when we take a sequence and we just add the terms. This is an infinite geometric series we're looking at, and it turns out that as we keep adding terms, sometimes we get closer and closer to some number. And the further we go out in that series and the more terms we add, the closer and closer we get to that number. That number is the limit. It's what we're approaching every time we add another term. When that series approaches a number called the limit, it is said to converge. It converges on that number. When the series keeps getting larger and larger as I add more and more terms, the sum goes to infinity, then that series is said to diverge. Converge means it approaches some number. Diverge means it goes to infinity. And the way we tell is by looking at the common ratio. Remember that when we talked about exponential growth and we talked about the common ratio, we used R for the rate and 1 plus R was the common ratio. We're not talking about the rate anymore, and we need a variable to stand for the common ratio, so we're going to just use R. R is not the rate, R is the common ratio. We find the common ratio just like we did with exponential functions. The common ratio, which we're now calling just plain old R, is the current term divided by the previous term. We can use any term but the first. So take a current term, about 1/4, and divide it by the previous term, 1/2. You're always going to get the same number in a geometric sequence and a geometric series when you take current divided by previous. Remember that when you divide fractions, you multiply by the reciprocal. This is 1/4 times 2 over 1. And 1/4 times 2 over 1, if we cancel, divide by 2, we get 2. Divide by 2, we get 1. Turns out to be 1/2. The way we tell whether an infinite geometric series converges or approaches some number is if the common ratio is less than 1. It doesn't matter whether the common ratio is negative or positive, so we better say the absolute value of the common ratio. As long as the absolute value of the common ratio is less than 1, then it converges. It approaches a number. If the absolute value of the common ratio is greater than 1, then each time I add another term, my sum gets larger and larger and it goes to infinity, and it is said to diverge. If the absolute value of the common ratio is less than 1, it converges on a number. If the absolute value of the common ratio is greater than 1, it diverges and the sum goes to infinity. An infinite geometric series, when it converges, meaning the absolute value of the common ratio is less than 1, is equal to the first term divided by 1 minus the common ratio. Let's take the sequence I have from the previous page. 1/2 plus 1/4 plus 1/8 plus 1/16. Every time I move along in this series, I'm multiplying by a half. The common ratio is a half. If you weren't sure what it was, reminder, you take the current divided by the previous. That's 1/4 divided by 1/2, which is 1/4 times 2 over 1, which is a half. The common ratio is a half. It's less than 1. So this thing will converge on a number. Every time I add another term in this sequence, I get closer and closer to some number. And that number is the first term, 1/2, divided by 1 minus the common ratio, 1/2. This ends up being 1/2 divided by 1 minus 1/2, which is 1/2. And anything divided by itself is 1. Every time I add another term in this series, I get closer and closer and closer to the value 1. Here's another example. This is a geometric series, and to find the common ratio, we would take the current, -4/5, divided by the previous, 8/5. This is -4/5 times, remember we multiply by the reciprocal, we're going to flip that second fraction, that'll be 5/8. The 5's will cancel, and these are both divisible by 4. Divide by 4, I get 2. Divide by 4, I get 1. Don't forget the negative. This ends up being -1/2. My r is -1/2. And the absolute value of r, that's 1/2, is less than 1. This will converge. We know this approaches a number. The sum, then, of this infinite geometric series will be the first term, 8/5, divided by 1 minus the common ratio, -1/2. This is 8/5 divided by, that'll end up being 1 plus 1/2, which is 3/2. This is 8/5, and I'll multiply by the reciprocal, times 2/3. That ends up being 16/15. Every time I add a new term in this series, I get closer and closer and closer to the limit, which is 16/15. One last quick example. Here's an infinite geometric series. Let's find the sum if it exists. The common ratio is the current, 1/8, divided by the previous, 1/16. This is 1/8 times, we're going to multiply by the reciprocal. We flip that second fraction, 16/1. That ends up being 2. Now, the absolute value of r, that's 2, is greater than 1. That means this series will diverge. It does not have a sum. The sum is infinite. It turns out that we can apply what we just learned to repeating decimals. We can find the fraction that a repeating decimal represents. To do that, what we do is take a repeating decimal and write it as a geometric series. 0.8, for example, 0.8888 to infinity, is 0.8 plus 0.08 plus 0.008 plus 0.0008. Notice we're multiplying by 0.1, but reminder, we could find the common ratio by taking the current, 0.08, divided by the previous 0.8, and that is 0.1. Since the absolute value of r is less than 1, this converges on some number. To find that number, we'll find s, the sum of this geometric series, by taking the first term, 0.8, and dividing by 1 minus the common ratio, which is 0.1. This is 0.8 divided by 0.9, and that would end up being 8/9. To simplify 0.8 over 0.9, I multiplied the top by 10 and the bottom by 10, and that moved the decimal one place on both of them. Multiplying by 10 over 10 is 1. It doesn't change the value of 0.8 over 0.9, and that's how come it's 8/9. One more example. We'll take 0.23, 0.232323, and write it as an infinite geometric series. 0.23 plus 0.0023 plus 0.000023, and so on. To find r, we would take the current, that's 0.0023, and divided by the previous, 0.23, that's going to be 0.01. If I divide that on a calculator, the sum will be the first term, 0.23, divided by 1 minus 0.01. That's 0.23 over 0.99. If I multiply the top and the bottom by 100, move the decimal 2 places, I end up with 23/99. Here's another way you can find the fraction for repeating decimal. Call that repeating decimal x. X equals 0.5 repeating. Then multiply by a power of 10 determined by the number of places that repeat. If one place repeats, you're just going to multiply by 10, 10 to the first. If 2 places repeat, you're going to multiply by 10 to the second, 100. If 3 places repeat, you're going to multiply by 10 to the third, 1,000. So I'm going to multiply x equal 0.5 repeating both sides by 10. When I do that, I get 10x equals, and when I multiply this by 10, it ends up being 5.5 repeating. Then you can write that other equation below, x equals 0.5 repeating, and subtract them. The repeating parts drop off, and I get 9x equals 5. And if I divide by 9, I can see that x equals 5/9. If you plug 5/9 in the calculator, 5 divided by 9, you'll see it's 0.555555 onto infinity. If we wanted to make 0.62 a fraction, we can call x equal 0.62 repeating, and I'm going to multiply by 100 because there are 2 places that repeat. Move the decimal 2 places. This becomes 100x equals 62.62 repeating. Write the other equation underneath and subtract them. 99x equals 62. Divide both sides by 99, and x equals 62 divided by 99. If you punch in 62 divided by 99, you'll see it's 0.62626262 forever. One last example. I'm going to call x equal 0.345 repeating. I'll multiply both sides by 1,000 because I have 3 places that repeat. 1,000x equals 345.345 repeating. Write the other equation underneath. Subtract them. 999x equals 345. And divide by 999. And x equals 345 divided by 999. By the way, occasionally you can end up with a fraction that reduces. This thing does reduce because both the numerator and denominator are divisible by 3. The divisibility rule for 3 is if you sum the digits and 3 divides the sum, 3 divides the number, the numerator 3 plus 4 plus 5 adds to 12, and the denominator 9 plus 9 plus 9 adds to 27, and both of those are divisible by 3. That rule works for only 3 and 9. If I divide both of those by 3, it reduces to 115 over 333. And if you punch that into the calculator, you'll see it is 0.345345 to infinity. The remainder of this video is questions from your assignment. Question 1. This series, does it converge or diverge? We'll take a current term to find r and divide it by the previous. That's negative 1/7 divided by 1, which is negative 1/7. Since the absolute value of r is less than 1, this thing converges. To find the sum, we'll take the first term, 1, and divide it by 1 minus the common ratio. That would be 1 minus 1 plus 1/7. 1 plus 1/7 is 1 and 1/7, which as a mixed number is 8/7. This is 1 divided by 8/7. When we divide fractions, we multiply by the reciprocal. 1 times 7/8, and 7/8 then is the sum. Every time we add a new term in this series, we get closer and closer to 7/8. Question 3, another geometric series. To find the common ratio, we'll take the current, -10/9, and divide by the previous one. That's -10/9. The absolute value of R is greater than 1. 10/9 is greater than 1. This thing then diverges. There is no sum, it is infinite. Question 6. We'll find the common ratio by taking the current, 5/2, divided by the previous one. That's 5/2. 5/2 is 2.5. The absolute value of R is greater than 1. This one diverges. And the sum is infinite. Question 7. Let's find the common ratio. We'll take a current term, -2/3, and divide it by the previous term, 1. The common ratio is -2/3. The absolute value of R, our common ratio, is less than 1. This will converge. To find the sum, we'll take the first term, 1, and divide it by 1 minus the common ratio. 1 minus -2/3 is 1 plus 2/3, which is 1 and 2/3. Make that an improper fraction. That is 5/3. When we divide fractions, we don't divide. We multiply by the reciprocal. 1 times 3/5, and this ends up being then 3/5. The sum of this series is 3/5. Question 8. Here we have a summation. The first thing we're going to do is plug in 1. This would be equal to -5/6. And when I plug in 1, it's 1 minus 1, so to the 0th power, plus -5/6. And I plug in 2, and 2 minus 1 will be 1. Plus, I'll plug in 3 for n. 3 minus 1 will be 2. -5/6 squared. And then I'll plug in 4. 4 minus 1 will be 3. -5/6 cubed. And onward. This equals 1 plus -5/6 plus +25/36 plus -125/6 cubed is 216. Now we want to find R. We know that R is the current, about -5/6, divided by the previous 1. That's -5/6. Since the absolute value of R is less than 1, this will converge. Now we'll find the sum. Sum is the first term. That's 1 divided by 1 minus the common ratio, -5/6. This would be equal to 1 times 1 and 5/6. 1 plus 5/6 is 1 and 5/6, which is 1 over 1 times 6 plus 5 is 11/6. I'll multiply by the reciprocal and flip that second fraction. 1 times 6/11, and that would be 6/11. 6/11 is the answer. Question 9, another summation. First we plug in 1. This is 6/4 to the 1 minus 1. That's to the 0th power. Then we'll plug in 2. 2 minus 1 is 1. Then we'll plug in 3. 3 minus 1 will be 2. On it goes. This is 1 plus 6/4 plus 36 over 16. That does reduce. Both of these reduce. To find R, we'll take the current. 6/4 is 3/2. 3/2, and we'll divide by the previous one, and we get 3/2. Since the absolute value of R is greater than 1, this one diverges. The sum goes to infinity. Question 20. We're repeating decimal. We can write that as a geometric series. This is 0.07 plus 0.0007 plus 0.000007 and onward. We'll calculate R. R is the current, 0.0007 divided by the previous. That's 0.07. This is 0.01. And the sum would be the first term, 0.07, divided by 1 minus the common ratio, 1 minus 0.01. This is 0.07 divided by 0.99. Multiply top and bottom by 100, move the decimal 2 places on both, and this is 7 over 99. The other way you could have done that is said that x equals 0.07 repeating. And since we have two numbers that repeat, the 0 and the 7, we multiply both sides by 100. 100x equals 7.07 repeating, and we don't need that 0. We subtract those, we get 99x equals 7, and divide by 99, and x is 7 over 99. Either way works fine. Question 23. Let's write 0.8 repeating as a geometric series. This is 0.8 plus 0.08 plus 0.008 and so on. We'll find R. It's the current divided by the previous. 0.08 divided by 0.8. This is 0.1. To find that fraction, take the first term, 0.8, and divide it by 1 minus the common ratio, 0.1. This is 0.8 over 0.9. If I multiply the top and bottom by 10 and move the decimal one spot, I get 8/9. Or you could say x equals 0.8 repeating and multiply the top and bottom by 10. Since there's one place that repeats, 10x equals 8.8 repeating. And this would be 9x equals 8. Divide by 9. X equals 8/9. Question 24. 0.45 repeating is what we have. I'll write this as a geometric series. 0.45 plus 0.0045 plus 0.000045. To find the common ratio, I'll take the current divided by the previous. This is 0.01. To find the fraction that is that repeating decimal, I'll take the first term, divide it by 1 minus the common ratio. 0.45 divided by 0.99. Multiply top and bottom by 100, and we get 45 over 99. I notice that both of these are divisible by 3. The rule for 3 is if you sum the digits and 3 divides the sum, 3 will divide those numbers. 4 plus 5 is 9, 3 divides into 9. 9 plus 9 is 18, 3 divides into 18. But hang on a sec. Actually, both of these are divisible by 9. The rule for 3 and 9 is the same. If you add them and 9 divides the sum, then 9 divides the number. These both divide by 9. You get 5 and 11. So our sum of our series is 5 over 11. The other way we could have done this is called x 0.45 repeating. Since there are two places that repeat, we multiply by 100. 100x equals 45.45 repeating. If I subtract those, the repeating parts drop out. I get 99x equals 45. And if I divide by 99, I get that 45 over 99. Both divide by 9, and I get the 5/11. Question 26. I don't really want to write this as a geometric series. I'm just going to use my technique of multiplying both sides by a power of 10. I need to figure out how many places repeat. 0.09863, 0.09863. Looks like we have 1, 2, 3, 4, 5 places that repeat. I'm going to call x 0.09863 repeating. I need to figure out my power of 10. 1, 2, 3, 4, 5. That's 10 to the 5th, or 100,000. Multiply both sides by 100,000. This is 0, 9, and the 0 doesn't matter. 863.09863, and we'll subtract, and those repeating parts will drop out. I get 100,000 x equals, I'm going to drop the 0, 9863. And we'll divide both sides by 100,000. This is my answer. Question is, does it reduce? Does it simplify? And I notice that neither of these are divisible by 3 or 9. It's not divisible both by 2 because this ends in a 3. It's not even. It doesn't divide by 5. And you could check some numbers like 7 and 11, some odd numbers, but I don't think that's likely to be the case. You could check this by plugging it in Desmos and hitting the little fraction circle button and making sure it's reduced. To me, it looks like our answer is right here.